This video is part 2 of an ongoing series. Click on the link at the top right or go to the link in the description for part 1. You can also subscribe to the Project Masquerade channel for updates on future videos. When we think of parkour in video games, we often imagine leaping from rooftop to rooftop, scaling massive buildings and performing some impressive acrobatics. This kind of fast and fluid motion throughout a vast open world is something that I hope to achieve in programming my own parkour system. But before we learn to run, we must learn to crawl. Before we can achieve the big, we must start with the small. Today, we'll be exploring the previously discussed field map and laying down the foundations for our own parkour system. Welcome to Game Mechanics Explored. Before we start programming, we'll take a look at the testing environment we'll be using in this video. This is the field map. It's a small, mostly flat environment without many obstacles in our way. The purpose of this map will be to simply establish player movement and some very basic parkour. As long as we can get from one end to the other, we're good. I have this low poly environment as a quick and easy way of visualizing a more complete representation of the final design. It doesn't take much work to make and allows me to test my code in a more accurate setting. We'll be doing the same for the other map types in later videos, as well as other mechanics that we'll be developing down the line. I also took this testing dummy that I found on the internet a while ago and gave him the same low poly treatment so that he fits in better. I also gave him a little face because why not? Before we can do anything related to the parkour system, our player needs to be able to actually move. This was something I programmed long before I ever considered making a parkour system, and it was pretty much my first real foray into programming. I used this very good tutorial series by Sebastian Lague, and I highly suggest you go check it out. I made a few changes to this over the years to make it fit with my own project, but I'll run you through the basics of how it works. The idea here is that, like a lot of games, we can control our player's rotation the standard way with the WASD keys, or in this case the left analog stick of our controller. We can also control the player's rotation by simply holding forward and moving the camera. This is achieved by taking the left analog stick's input values, represented by the X and Y coordinates, X for the horizontal axis and Y for the vertical axis, and converting them into its equivalent angle in degrees, and adding that converted value to our camera's Y rotation value, giving us a target rotation. We then smoothly transition from our current rotation to our target rotation each frame, allowing us to turn with the left analog stick. As for actually moving, we create a scaling value for our speed by converting those input coordinates into a single value. The value goes from 0 to 1, 0 representing our analog stick at the center, not being moved, and 1 representing the analog stick being pushed as far from the center as it can go. This allows us to adjust our speed by adjusting the left analog stick's position. With our target speed value, we can then call Unity's character controller move function and apply the arguments of our player's current speed and forward direction over a given time. I skipped over a bunch of boring physics stuff there, but all you need to know is that we now have some very simple but very nice movements to work with. Again, I recommend that you go check out Sebastian Lague's videos. He explains it more in depth, and I didn't include everything from his tutorials, just the stuff I needed to get my player walking around. To expand upon this, I wanted to add a few more things to the code to make our animations a little more realistic. Things like leaning into turns and accounting for sharp movements of the left analog stick. I did this by lifting a value from Sebastian's original code, namely this ref value called turn smooth velocity, and seeing how it behaved when I turned the left analog stick, mostly because I don't actually know what it does. What it told me was how fast I was rotating my player character, presumably in degrees per second. This gave me a great scale for adjusting my animation and how hard my character leant into their turns. I know the numbers are kind of going crazy here, but they tell me that the harder I turn, the higher the number. Therefore, the higher the number, the steeper I can make the leaning animations. A convenient side effect of truncating this value from the input coordinates was that I could tell if the lean should go right or left by checking if the turn smooth velocity value was a negative or positive number. It's definitely quite a subtle effect, but a nice one nonetheless. I could also use a large spike in this value to trigger a quick turn animation, as I found that reaching a value over 180 degrees was elicited by sharp movements of the analog stick, as opposed to the smaller rotations when leaning into turns. But I can always add that in later. I may expand upon this in the future by having more realistic transitions between animations, such as actually slowing down to a halt, rather than having Unity's blended animations simply transitioning me to an idle pose. For now though, I don't have those animations, so we'll just have to move on. To parkour around any environment, our player needs a way of seeing what we're seeing. After all, the player in-game only has the information and instructions we can feed it through code. I mean, just look at him, he doesn't know anything. Even with our simple movements so far, the player doesn't know anything about its surroundings and needs to be provided a way of deciphering the near vicinity to be able to make decisions, particularly when it comes to parkouring around. Take this fence for instance. It's reasonable to assume that we could just jump over that fence, but it's not that simple. The player only has the logic that's programmed into it, which right now consists of basic movements. They don't know anything about this fence, and therefore we can't tell the player how to jump over it. We need a way of not just scanning this fence, but scanning the immediate area around the player to receive information relevant to the parkour system. I did this by creating the platform scanner. I made use of a variant of something called a raycast, which is essentially like a laser beam that receives information about the thing that it collides with, such as the name of the object and the position of the point of collision, among other bits of useful information. The variant I used is referred to as a spherecast, which gives me a larger area of collision and allows me to use fewer rays for scanning. By creating two boundaries and generating an array of spherecasts that scan forward from the player at incrementing heights from the player's feet to above the player's head, I can receive another array of information pertaining to what and where, if at all, those spherecasts hit. Users of the Unreal Engine might know spherecasting as sphere tracing, but it's all the same idea. See those blue spheres at the end of those lines? I know, and more importantly, the player knows, where those spheres are. These spheres, or raycast hits, as they're called in code, can be sorted to give us the lateral position, or X and Z coordinates, of the nearest obstacle. The raycast hits are sorted by finding the shortest distance produced by an array of casts, and of the casts whose distances are equal to the shortest value, we find the cast with the highest index, or in other words, the highest position in the array. Let's say we cast an array of 15 sphere casts out from the player's forward direction, with the lowest index at the player's feet and the highest just above the player's head. Some of the lowest ones hit an obstacle. The information that we want to receive about this obstacle is tied to the edge that is facing us, some information that we need to interact with. We get the shortest distance because we'll always want the information from the obstacle that is closest to us, and we always want the highest index because it will be the closest cast to the edge of the obstacle. This is our lateral scan, shown here by the red sphere. From here, we can send out another sphere cast downwards to ascertain the final y coordinate of the edge of the obstacle, giving us a point in 3D space for our player to anchor themselves to should they need to interact with said obstacle. For now, we'll call this coordinate the scan point. By having different bits of information about our scan point, such as its distance and angle from the player, and its height compared to the player, we can now begin structuring our player's parkour logic. Another thing to note is that this system is completely dynamic. Objects require little additional setup when being placed into a scene, something that plagued past attempts at this system. Okay, so our player now has the information they need to jump over this fence. So we aren't so much climbing this fence, we just want the player to jump over it. It's important to know that there has to be a clear distinction between platforms that we expect to climb onto and hang from, and obstacles that we climb over. The main difference will obviously be height. I found that the best height was anything that went below the player's head, which was a value of about 2. We'll be working on every kind of movement that can take place below this height boundary. Everything above that boundary will be worked on in future videos. Then we set a minimum distance. If the player comes within a certain distance of our scan point, then they're close enough to jump over the fence. I found a distance of about 0.75 to work nicely. The last thing we look for is the angle. It wouldn't make much sense for our player to jump over this fence if they were running against it like this, so we also receive an angle value from our scan, and set a condition in our code that the player can't jump over this fence if the angle is too low. The last thing we check for, specifically in regards to these obstacles, is depth. It's all well and good jumping over a simple fence, but this is a dynamic system, and you have to remember that the player doesn't actually know what's in front of it. It only has a series of numbers to work with. By checking and comparing these numbers, it's only able to understand what the thing in front of it might be. It's up to us as programmers to feed it the best information and perform the right checks so that the player can narrow it down as much as possible without making the script completely unreadable. The player doesn't know that this obstacle is a fence. It only knows that it's about this height, it's this far away, and what way we're facing it. Depth will further differentiate this fence from another type of obstacle entirely, meaning we won't perform the incorrect movement on the other type. If it doesn't return, then the platform has no depth, as you can see here. Now that we have our checks performed and everything looks right, the player can execute a jump over this fence. This is done by having a couple of animations for jumping over an obstacle, all with different heights. By blending between these animations, using the height variable we received earlier, the player will climb over the wall with enough clearance to avoid having the colliders catch on the obstacles. During this animation as well, we freeze the player's control over their position and rotation to stop them from moving around when they shouldn't be. After the height of the jump, the second half of the animation begins to play, and we can begin resetting the relevant settings. Once the player is back on the ground, they can keep moving as normal, by resetting the trigger for the animation. For platforms that exceed our minimum depth, we have a similar method where the player is simply moved while the animation plays. From here onwards, we'll be referring to these movements as vaults. Where the depth value is under our boundary, we'll be vaulting over, and where the depth value boundary is exceeded, we'll be vaulting onto. These movements, combined with our platform scanner, form a strong basis for our parkour system going forward, as well as giving us some nice simple movements to pull off in this relatively barren environment. Now, rather than running around and trying to find a gap in these fences, we can just jump over them. Rather than going the long way up this hill, we can just climb up these conveniently parkourable rocks. The next thing we have to do is what we discussed in the introduction video, deciding whether or not these movements will be standard or context inputs. If we're running full bore at a wall, then we can assume that the player doesn't intend to smack into it. So if every other condition is met, and we get close enough, we can let the game take over and let the movement play out. If we're just sidling up to a wall at a walking pace, it would be better to let the player decide if they want to climb up or not. If we're running, it's a context input. Every other time, it's just standard. The only problem here is one that I've brought up before, and that's animations. I bought these animations from a Unity asset pack that is no longer available, and when it comes to this system, my options are now only slimmer. I have an animation for vaulting over obstacles and onto platforms, but you'll notice that I only have 1 or 2 per movement. Both are absolutely fine and look correct when the player runs towards a platform. But I have no other animations for the player if they're walking, or clearing the obstacle while they're in cover, which we'll take a look at in a moment. I'm limited in what I can effectively do with this system until I have a better range of animations, and while this asset pack was great in getting me this far, it still wasn't enough. Not only will I need to replace these animations with my own in the future, I'll need to make my own to fill in the gaps that I couldn't before. Maybe in a future video, we'll explore animating a 3D character, or setting up some DIY motion capture, but for now, there are plenty more mechanics we can work on in the meantime. We now have a couple of ways for our player to climb up and over small obstacles, but what goes up must come down. We need to create a way for our player to not only interact with the obstacles in front of them, but also the obstacles that aren't there at all. Luckily, a majority of the information we need to construct our logic here can be received from only a couple more raycasts pointed at the ground. First thing we need to know is if the player is actually on the ground by casting directly down from the player's feet and checking the distance. If the distance is low enough, we can assume that the player is at least close enough to the ground to be classed as standing on it. With another cast pointed downward, slightly in front of our player, we can check the ground immediately in front of them. If the distance is roughly equal to the previous cast, then we can assume that there is still floor where the player is headed. If the distance suddenly skyrockets, then we can assume that the player is standing on the edge. Again, height is our major variable here. If the drop is high enough to hurt or kill the player, then we have another instance where it's best to let the game take over and decide what to do for us. In this case, we want the game to stop us from walking off an edge. When the downward cast determines that the player is close enough to the edge, we set the player's target speed to 0, stopping them from falling off. And because the movement is based around rotating the player according to the left analog stick, we're still able to turn around and have our target speed reset. While our edge stop is active, we can now give the player the opportunity to interact with the edge, depending on the geometry. If there is too much of a drop, and if there is enough clearance, we can let the player drop to hang from the edge. Stay tuned for part 2 for that. If the drop isn't too high, or there isn't enough clearance, then we let the player just step off the edge, with the actual movement itself being dependent on the height they need to travel, using a similar method to the vaulting animations and blending between them. We can of course override the edge stop entirely by running at the edge and triggering a jump where the stop would have occurred otherwise. Save for a little bit more tinkering, this is pretty much as far as we can go with these movements. We can jump over things, climb onto small obstacles, and get back down again. We can stop our player from falling into the abyss, or we can yeet ourselves into it for fun. As far as parkouring around below our height boundary goes, we're pretty much all set, at least with the important stuff. One last thing to make before we move on is a small addition to make our animations look more realistic. IK, or inverse kinematics, is a very complicated name for a very simple idea. Without going into the mathematics behind it, IK in the context of video games is used to override an animation's preset movement parameters and allows developers to control different parts of the model free from the boundaries of the animation. Basically, we can have the player's walking animation play out as normal while applying IK to the arms. It doesn't matter what the animation is telling the arms to do, with IK applied, they can be controlled to do other things. You might be more familiar with IK and its effect on feet in other video games, making sure that they actually look like they're on the ground rather than floating randomly in the air because the animation said so. IK can be applied to any body part on our player, but we'll mostly be using it for the arms and hands in this system. By using a similar setup to our platform scanner, we can have two smaller scans around our earlier scan point. The points received from these two scans will become the positions that will tell the IK where to place our hands during certain animations. We'll see this used to greater effect in the next video, but we can still use it here to really tie together these animations. Like leaning into turns before, the effect is very subtle, but it's better to have it than to not have it. It'll take a little more messing around with, but because it's kind of a cosmetic thing, it's not really a priority at the moment. I referred to the player taking cover earlier. While the cover system isn't really involved with parkour, the two do cross over sometimes. The reason I'm including it here is because it'll come up later when we develop another mechanic, and because it's a good example of just how versatile our platform scanner can be. When we get close enough to a wall, we can tell our player to back against it and go into cover by pressing the R1 button. We can then press it again to leave cover. While in cover, the system ensures that as the player moves along the wall, they're always kept at a certain distance away from it. Essentially, any wall becomes like a track for the player to move along. With our array of sphere casts, we constantly monitor the height of the wall that we're taking cover behind, meaning we can set up an automatic transition between standing behind a wall and crouching behind it. We'll see more uses of this system in a future video. As I've said before, I'm limited by the animations I have to hand, because a lot of finer details in the code revolve around how the animations behave. If I don't have an animation to work with, I don't have a movement to program. It's that simple. Aside from the things I've talked about earlier, there are more additions we can make to this relatively simple basis to further flesh it out. We're just unable to do them at present without the necessary assets. The first one is a wider range of vaulting animations. I was never able to develop these movements as fully as I like, because I only had a small handful of animations to work with. Ideally, I'd have a couple of animations that I can cycle through per movement, just to give everything a bit more visual variety. On top of this, having vaulting animations for different player speeds will really help bring a greater amount of depth to these simple mechanics. Another mechanic I wanted to make was allowing for the player to run into cover by sliding before they hit the wall and jump over or onto it. I have a sliding animation, but unfortunately I don't have anything that could realistically transition from sliding to a cover animation, and the animation isn't the greatest either. The code would be pretty simple, but without a transition animation to act as a condition for changing a few settings, I open the mechanic up to glitches. If the settings aren't changed at a particular time, the player doesn't successfully transition to cover, instead simply cancelling both the slide and the cover transition entirely. By having an intervening animation between them, this problem is solved. I also wanted to use sliding as a way for the player to stop themselves from automatically jumping from the edge of a platform. By quickly sliding before reaching the edge, the player would grab the edge and hang from it, allowing players to climb back up. But again, without animations, I'm stuck on just how far I can go with this system. Apart from these few quality of life additions, the parkour system in our field map is pretty much complete. We now have a way of simply moving around and interacting with small obstacles, as was intended. There isn't much else we can do here in this map without diving into the realm of things like player upgrades, but they can always come later. For now, the parkour system serves to give us just that little bit more flexibility when it comes to how we get around our chosen map. So if I'm able to squeeze in another mechanic into this particular map, I'll showcase them in a future video. This version of the system and the code behind it is somewhat of a refactor from the last version seen in my old parkour showcase. The fact of the matter was that the old script had all the logic it needed, but it was kind of all over the place, and as it became larger and more complex, more and more things would start to break and function incorrectly. While I could have just taken the time to straighten everything out, the script had just become too big to fix in a somewhat timely manner. Instead, I simply kept the same logic and rebuilt the code in a new script. So far, just with this small part of the system, it has proven rather effective. I have a really solid basis for my parkour system that does far more than the equivalent mechanics in the old script. And I somehow managed to do it with a fraction of the code. I just want to make a point here, that the system that you're seeing now has been a long time in the making, and while you're seeing the end result, I cannot overstate the sheer amount of failures that led to these results. The old code worked, just not very well. But it still worked, and probably still does. My very first attempt, however, completely stopped working after a couple of days, and at the time I just didn't know why. I wasn't good enough to fix it. I have spent more time than I probably should have making this one system, but it has been a trial by fire, if nothing else. I'm definitely a better programmer than I was during the first attempt, and I only got better by knowing that my code sucks and can be improved. I'm reasonably confident that this will be the last version of the system that I make, but who knows? Maybe in another 2 years I'll look back on the video and cringe myself silly over my terrible code. Maybe I'll have made another few attempts at the ever-evasive parkour system. Or maybe, just maybe, it'll work just fine. Now that we have a platform scanner set up and some basic movements under our belt, we can move on to our next map. Next time, we'll be further expanding our parkour system by giving our player a greater understanding of their surroundings and giving them the ability to climb. As always, you can go to the Project Masquerade channel for more game design content, and you can subscribe for future videos. Thank you for watching, and I'll see you next time.